October 20th, 2025, a recently unveiled image of 3-Eye Atlas sent researchers into a frenzy, deepening an already perplexing enigma. The photograph captured 3-Eye Atlas expelling a 6,000-kilometer stream that pointed directly toward the sun instead of away from it. This extraordinary occurrence is so peculiar and atypical that it strongly suggests a manufactured origin, not a natural one. What precisely is this entity? Is it truly a comet? Tonight we will meticulously dissect all the gathered evidence. And by the conclusion, our findings will not only revolutionize our understanding of cometary physics, but also unveil a truth for which no one is prepared. If these mysteries intrigue you as much as they do me, don't merely observe, become involved. Click the like button and subscribe to ensure you're alerted to every development as this narrative unfolds before our eyes. In the comments section, share your location, the current time there, and your thoughts on whether we are being presented with the complete truth or merely a curated version. To broaden this discourse, please share this video on X, Facebook, Reddit, or even within your private messages. This channel thrives because of your engagement, and your backing empowers us to continue investigating the mysteries that others shy away from. Part 1. The Image That Should Not Exist. On October 20th, 2025, the astronomical community was profoundly shaken by an event deemed impossible. A depiction emerged within the Astronomers' telegram, processed from data acquired on August 2nd and 3rd by the twin telescope, the Tidy 2-meter, located in the Canary Islands. The visual presented was so fundamentally flawed, so contrary to established physical principles, that astronomers worldwide paused in their work, transfixed. Envision this image in your mind. At its core, a dark, circular mask obscures the intense radiance of the celestial body itself. Encircling this mask is a brilliant aura, the anticipated dusty coma that envelops any genuine comet. However, extending from this cloud of gas and particulate matter is something else entirely. A slender, faint, yet undeniable jet, stretching approximately 6,000 kilometers in projected length. And this is where physics seems to take a holiday. This jet is directed precisely at the sun. You might be thinking, so what? Comets frequently exhibit jets. They are spectacular, dramatic phenomena where material is ejected into space as frozen volatiles vaporize under solar heat. But here's the critical point, a fundamental concept every undergraduate astronomy student grasps in their introductory planetary science course. Comet jets invariably, and I stress invariably, point away from the sun. This is not a matter of preference or tendency. It is a direct consequence of how radiation pressure and the solar wind operate. The sun exerts a repulsive force, and matter flows outward. The underlying physics is as straightforward as water flowing downhill, except in this instance the water appears to be flowing uphill. The jet emanating from 3-Eye Atlas, this interstellar visitor that has captivated observers for months, fundamentally defies this established principle. Imagine witnessing a fountain where the water arcs backward into the spout, or observing smoke from a fire drifting down into the flames. That is the degree of anomaly we are confronting. The anti-solar region, the very zone where jets and tails are expected to form, remains empty or subdued. Meanwhile, this sunward plume extends like an accusatory finger towards our star. Scientists operate within theoretical frameworks. We construct models that elucidate observed phenomena, forecast future events, and occasionally, these models collapse when nature unveils something unforeseen. This image does not merely challenge the prevailing comet model, it shatters it. If this feature is indeed real, not some elaborate fabrication of image processing or an observational error, then we must revise our understanding of the behavior of these ancient celestial wanderers. The implications spread like fissures in ice. Are we observing an entirely new category of celestial object? Is some exotic physical process at play, one we have never encountered in the comets of our own solar system? Could this be evidence of something even more extraordinary, something that renders the term comet insufficient for what we are witnessing? These questions currently lack definitive answers, and it is precisely this uncertainty that makes this moment so exceptional. Before we delve deeper into the ramifications, we must address the obvious elephant in the observatory. Astronomical images, particularly those derived from faint signals through sophisticated processing techniques, can be misleading. They can depict phantom phenomena, artifacts, and patterns that exist only in mathematical representations rather than in physical reality. Laplace filtering, the method employed to enhance faint structures in this particular image, is a powerful tool, but it is not infallible. It can amplify noise and even generate spurious features from the streaking of background stars during long exposures. Every competent astronomer is acutely aware of this. Consequently, the initial reaction to any startling image is a healthy degree of skepticism. Therefore, we will not accept this depiction at face value. We will demand corroboration, multiple independent observations utilizing different instruments and methodologies, all converging on the same conclusion. However, I can confidently state that such corroboration already exists. It has been accumulating for weeks. Earlier observations had already hinted at plumes extending at unusual angles, at position angles around 280 degrees that deviated from expectations. The Hubble Space Telescope has captured fleeting glimpses of asymmetrical features. Ground-based observatories in numerous countries have detected indications of the same orientation. This is not an isolated incident with a single telescope. This represents multiple instruments scrutinizing the sky, employing diverse technologies, all perceiving a similar phenomenon. The scientific community has not yet reached a consensus of absolute certainty. Such certainty is a rare luxury in science, but the prevailing sentiment is shifting from likely an artifact to probably genuine to we must account for this. When astronomers begin publishing research papers that address the sunward jet as a legitimate phenomenon requiring genuine explanations, it signifies that a threshold has been crossed. We have moved from doubt to acceptance, from dismissal to fascination. What transpires next will determine whether this object necessitates a fundamental redefinition of our understanding of small celestial bodies, or if it opens entirely new avenues of inquiry. Time is of the essence. Within days, two spacecraft will traverse nearby space, their instruments potentially gathering data that could either validate or invalidate our interpretations. But before that pivotal moment arrives, we must comprehend the full depth of this unfolding mystery. Because the solar jet, as striking as it is merely the beginning. The chemical composition of the material being expelled from this object tells a story that makes the jet appear almost commonplace in comparison. Part 2. Confirming the sunward plume. Before we embrace the improbable, we must exhaust every plausible, mundane explanation. This is both the greatest strength and the most frustrating requirement of the scientific method. When confronted with the extraordinary, our initial imperative is not celebration, but scrutiny. Therefore, let us scrutinize with informed doubt. Image processing in astronomy is a blend of artistry, scientific rigor, and forensic investigation. We are dealing with photons that have traversed interstellar distances, impacted a detector, been converted into electrical signals, and are now subjected to mathematical manipulation to reveal structures too faint for direct visual perception. Each stage presents potential avenues for error. Background noise can be mistaken for genuine features. Cosmic rays striking the detector leave bright trails that can resemble jets. The movement of stars across the frame during long exposures can create linear patterns that might coincidentally align with intriguing directions. Deconvolution algorithms, designed to sharpen blurred images, can introduce artifacts that generate false structures. The teams analyzing 3i Atlas are well aware of these potential pitfalls. They possess decades of experience in this field. They did not simply apply a filter and declare their work complete. They meticulously checked for interference from background stars. They examined multiple observation periods to ascertain whether the feature persisted or changed in a manner consistent with a real physical plume rather than a processing artifact. They compared results obtained from different telescopes, each equipped with distinct optical systems, detectors, and operating under varying atmospheric conditions. They scrutinized the raw data prior to any processing, searching for the subtle signals that would confirm the existence of something tangible before algorithmic enhancement. What emerged from this rigorous process of skepticism was increasingly difficult to disregard. Earlier observations from late July and early August had already indicated the presence of unusual plumes extending at position angles that were inconsistent with typical cometary activity. Position angle, for those unfamiliar with the term, is a measure of direction on the celestial sphere, with 0 degrees indicating north, 90 degrees east, and so forth. The anti-solar direction, where comet tails conventionally point, has a predictable position angle based on the geometric alignment of the comet's orbit and the Sun's position relative to 3i Atlas. During those observations, this anti-solar direction should have been nowhere near the location where the jet was observed. Multiple research groups commenced cross-referencing their data. The Hubble Space Telescope, renowned for its exceptional resolution above Earth's atmospheric turbulence, had captured images revealing asymmetrical coma structures. Ground-based observatories situated in Spain, Chile, and Hawaii independently identified anomalous features. None of this occurred in isolation. Astronomers engage in collaborative dialogue, share data, and compare their findings. When numerous independent teams begin to detect similar anomalies, the explanation of an artifact becomes progressively less tenable. Consider it analogous to eyewitness accounts of an unusual event. If a single individual reports seeing something strange, skepticism is warranted. However, if 10 individuals, dispersed across a city, all describe witnessing the same peculiar event from different perspectives, using different recording devices, and at slightly varying times, yet their accounts contain consistent details, then it becomes imperative to take their testimony seriously. This is the current situation with the Sunward jet. An overwhelming number of observations, instruments, and a remarkable degree of consistency. The technical specifics are crucial here, as they differentiate between unsubstantiated speculation and empirically grounded observation. When scientists employ Laplace filtering, they are essentially identifying edges and abrupt changes in brightness. It is akin to increasing the contrast on an image to make faint details perceptible. However, this technique is well understood. We are aware of the artifacts it can produce and possess methods for distinguishing between genuine features and false impressions generated by the filtering process. The Sunward jet exhibits characteristics consistent with a three-dimensional structure extending from the nucleus, rather than a two-dimensional processing artifact. Some researchers have gone further, analyzing the spectral signatures of the material in different regions of the coma. If the jet is real, its spectrum should display the same molecular emissions as the rest of the coma, albeit potentially in different proportions, depending on what is being preferentially ejected. Indeed, spectroscopic data has corroborated the presence of material in that sunward direction, not merely empty space with background noise. It is exceptionally difficult to fabricate molecular emission lines. Either the molecules are present, fluorescing in sunlight, or they are absent. So, where does this leave us? The scientific community has transitioned from initial disbelief to a posture of cautious acceptance. Research papers are now being authored, proceeding under the assumption that the sunward jet is a genuine phenomenon and focusing on its explanation rather than attempting to dismiss it. This represents a significant shift. It signifies that we have crossed the threshold from questioning its reality to acknowledging its probable existence. So, what does it signify? And this latter question is considerably more intriguing and far more unsettling. Because if the jet is real, if material is genuinely streaming towards the sun, defying everything we believed we understood about cometary physics, then we must investigate what this material is. We must examine its chemical composition, its constituents, the unique signatures of whatever substance is generating this retrograde expulsion. And when we direct our spectrometers towards 3I Atlas and analyze the light it emits, we discover something nearly as perplexing as the jet itself. We find nickel where iron would be expected, carbon dioxide instead of water, and ratios that defy the norms for a typical comet. While the jet may be the most visually arresting anomaly, the chemistry is where the situation becomes truly extraordinary. Part 3. Nickel in the absence of iron. If the jet is indeed real, and our confidence in this is steadily growing, then the next logical inquiry becomes inescapable. What precisely is being ejected from this object? When we examine comets, we are essentially performing remote forensic chemistry. Sunlight interacts with molecules in the coma, elevating them to higher energy states. As they return to their ground states, they emit photons at very specific wavelengths. Each molecule possesses a unique spectral signature, as distinct as a barcode. By dispersing this light into its constituent colors and measuring the intensity at different wavelengths, we can identify the chemical compounds present and their relative proportions. Astronomers have employed some of the world's most powerful spectrographs. The Very Large Telescope in Chile, equipped with a UV spectrograph, has captured high-resolution spectra across multiple observation periods as the comet approached the Sun. The revelations from these spectra were, to put it mildly, unexpected. Prominent emissions from neutral nickel atoms were observed in specific portions of the spectrum. This was not a subtle hint or a marginal detection. It was a clear, unambiguous signal proclaiming nickel is present. While the presence of metals in comets is not inherently astonishing, comets do contain dust grains, and these grains incorporate refractory elements such as iron, magnesium, sodium, nickel, and calcium. When dust vaporizes or under conditions of intense solar radiation, these metals can enter the gaseous phase and emit their characteristic spectral lines. What is remarkable about 3I Atlas is the proportionality. Specifically, the ratio of nickel to iron is highly anomalous. In typical solar system comets, the detection of nickel is invariably accompanied by the detection of iron, and in ratios that generally align with cosmic abundances. Iron is more prevalent than nickel in the universe, more common in meteorites, and indeed, in virtually all astronomical contexts we have studied. One anticipates observing more iron than nickel, not the reverse. Yet, in 3I Atlas, observations have revealed periods where nickel emissions were strong, while iron emissions were virtually undetectable, not merely diminished, but absent, missing in action. The scientific terminology for this is an extreme abundance ratio. In lay terms, this signifies something profoundly unusual. Certain observations have indicated nickel to iron ratios that are orders of magnitude higher than anything previously observed in other comets. It is as if a typical comet were subjected to a selective process that carefully removed most of the iron, leaving the nickel behind. Nature typically does not operate with such discriminatory precision. However, the chemical peculiarities do not end there. The James Webb Space Telescope, a marvel of infrared astronomy that is currently revolutionizing our perception of the cosmos, has also been directed towards 3I Atlas. JWST excels at observing infrared wavelengths, making it ideally suited for detecting molecules such as water, carbon monoxide, and carbon dioxide. Its findings indicated a coma dominated not by water, as would be expected from a conventional comet, but by carbon dioxide. The ratio of carbon dioxide to water was approximately 8 to 1. Let me reiterate, 8 times more carbon dioxide than water. For context, most comets in our solar system are essentially dirty snowballs, with water ice being the predominant volatile substance. While they do contain carbon monoxide, carbon dioxide, methane, ammonia, and other frozen gases, water typically prevails by a significant margin. It is the substance that vaporizes most readily at the distances where comets typically become active. Comets exhibiting high carbon dioxide ratios are rare, and even among these unusual cases, an 8 to 1 ratio stands out as extreme. What could be the cause of such peculiar chemistry? Scientists have immediately begun proposing natural mechanisms. One intriguing hypothesis involves metal carbonyl compounds. These are molecules in which metal atoms are bonded to carbon monoxide groups. Nickel tetracarbonyl, with the chemical formula NiCO4, is a real chemical compound that forms under specific conditions. Iron pentacarbonyl, FeCO5, is its iron counterpart. Both are volatile, meaning they can sublimate at relatively low temperatures compared to pure metals. If 3 Atlas somehow contained these compounds, their decomposition could release nickel and iron atoms along with carbon monoxide. The challenge lies in the specific conditions required for their formation and their stability over the billions of years this object has spent in interstellar space. Metal carbonyls are not particularly stable. They decompose when exposed to ultraviolet radiation, which is abundant in space. Their formation necessitates cold, reducing environments. Could 3I Atlas have originated in some exotic stellar environment where these compounds were prevalent? Perhaps in the vicinity of a carbon-rich star or within a molecular cloud exhibiting unusual chemistry. This is conceivable, but it remains speculative. Furthermore, it does not fully account for the nickel-to-iron ratio. Even if metal carbonyls are implicated, why would nickel carbonyls sublimate preferentially over iron carbonyls? Their sublimation temperatures differ, but not dramatically. Therefore, a very specific thermal environment within the nucleus would be required to facilitate the expulsion of nickel while retaining the iron. And subsequently, as the comet draws closer to the sun and temperatures escalate, iron should begin to appear, which, according to some observations, it does. Researchers have noted that iron emissions only became detectable when 3I Atlas crossed within approximately 2.64 astronomical units of the Sun. This aligns with a temperature-dependent release mechanism, but it presupposes a very specific layering or compositional gradient within the nucleus. Some researchers, likely during late-night discussions over coffee in observatory common rooms, have begun to cautiously entertain more exotic possibilities. What if a portion of this object is not natural in origin? What if we are observing materials that have undergone processing or engineering? Nickel alloys are ubiquitous in human technology, from stainless steel and high-performance turbine alloys to corrosion-resistant coatings. Nickel cyanide chemistry is utilized in electroplating processes. If one were to construct a spacecraft or probe designed for interstellar longevity, nickel-rich alloys might be selected for their exceptional strength and resistance to corrosion. This is precisely where we must exercise extreme caution. The leap from anomalous chemistry to an extraterrestrial artifact is immense and demands extraordinary evidence. We possess anomalous chemistry. We do not yet possess extraordinary evidence. However, the question persists, an uncomfortable yet tantalizing presence in every presentation and research paper. If this chemistry is natural, it indicates that our models of comet formation are incomplete. If it is not natural, then we are engaged in a fundamentally different discussion. The compositional anomalies do not exist in isolation. They are interconnected components of a broader pattern, a web of peculiarities that includes the sunward jet, unusual activity patterns, and other oddities that we are only beginning to catalog. When anomalies accumulate, when enough discordant elements begin to surface, a tipping point is reached where dismissing each one individually becomes more challenging than confronting them as a collective puzzle. And speaking of patterns, there is one further aspect of 3 Atlas's behavior that resists easy explanation. This object does not merely emit gas randomly, it pulses. Part 4, the 4-hour pulse. The object does not expel gas into space in a gradual, continuous manner as we typically expect from sublimating ice. Instead, it does so with remarkable regularity. Observers monitoring 3I Atlas have detected periodicities in its brightness and outgassing activity, rhythmic variations that repeat approximately every 4 hours. Some data even suggests a 2-hour period, possibly harmonically related. Imagine a heartbeat, a consistent pulse that suggests an underlying mechanism driving activity in an on-off cycle, with almost mechanical precision. In natural phenomena, such regular periodicities are typically attributed to rotation. The most straightforward explanation for a comet exhibiting a 4-hour activity cycle is that its nucleus rotates with a 4-hour period, and active regions on its surface are alternately exposed to and hidden from sunlight as it turns. This scenario is not unheard of. Many comet nuclei are irregularly shaped, elongated masses of ice and rock that tumble through space. If jets are concentrated in specific areas, perhaps where volatile, rich deposits are exposed or where the surface structure funnels gas preferentially, then as the nucleus spins, those jets would appear to switch on and off relative to our line of sight or solar illumination. This is a perfectly reasonable, perfectly natural explanation. Comets known to experience periodic outbursts exist. The rotational explanation makes sense, and if that is all that is occurring here, then the 4-hour pulse is interesting, but not revolutionary. It provides information about the nucleus's shape and the distribution of its activity, adds to our comprehension of this specific object, but does not challenge fundamental physics. However, let us delve deeper into what this explanation necessitates. For rotation to yield a clean, consistent 4-hour signal in brightness and gas production, a highly uniform active region or a very specific geometry is required. Minor irregularities in the nucleus's shape, uneven heating, and changes in the subsurface ice distribution as volatiles are depleted should all introduce noise and variation. Yet, the observations indicate a remarkably stable periodicity. While not impossible, this is noteworthy. It suggests either that the nucleus possesses a surprisingly uniform pattern of activity, or that whatever is driving the outburst is self-regulating in some manner. Another natural possibility involves a binary nucleus, meaning 2 chunks of ice orbiting each other. If the orbital period is 4 hours, tidal forces and mutual heating could induce periodic fluctuations in activity. Binary comets and asteroids have been observed. Their physics are well understood. If 3I Atlas is a contact binary or a separated binary, this could account for the periodicity without resorting to anything unusual. However, again, a rather specific configuration would be needed, and we lack direct imaging of the nucleus to confirm or refute this. The object is too distant and faint for even our most powerful telescopes to resolve its nucleus directly. There is also the matter of observational bias. Periodicities can arise as artifacts of how data is sampled. If telescopes observe at regular intervals due to scheduling constraints or Earth's rotation, they might impose a spurious periodicity on noisy data. Astronomers are aware of this and attempt to correct for it using statistical techniques, but it remains a persistent concern. Could the 4-hour period be a real signal in the data, but not a real phenomenon of the comet? Possibly. The fact that multiple independent observing campaigns appear to detect consistent timing argues against it being purely an artifact. Nevertheless, caution is warranted. Now, let us consider the more speculative possibilities, interpretations that extend beyond standard cometary physics. If the 4-hour pulse is genuine and not simply explained by rotational binarity, what else could be its cause? Could there be some internal mechanism, a reservoir of volatiles periodically released through a controlled vent? In a natural comet, internal pressure builds as ice sublimates beneath the surface, eventually breaching weak points and causing outbursts. However, these outbursts are typically chaotic and irregular, driven by fractures and collapses that do not follow precise schedules. A regular, sustained 4-hour cycle suggests either an extraordinary coincidence of natural factors or something more organized. Imagine if the nucleus possessed internal structure, chambers or pockets where gas accumulates and is then released when pressure reaches a certain threshold. If these chambers were of similar size and the sublimation rate remained steady, periodic releases might occur. This is analogous to a geyser where groundwater heating follows a predictable cycle based on reservoir size and heat input. However, comets are not geysers. They do not possess stable underground cavities or regulated heat sources. They are agglomerations of ice and rock, porous and crumbly, not plumbed systems with valves and chambers. Unless, and this is where we venture into speculative territory, the object incorporates some engineered component. If part of its structure includes materials or design elements intended to regulate gas release, one could envision a periodic cycle driven by intentional mechanisms, vents that open and close, reservoirs that fill and empty, systems designed to maintain pressure or ration volatiles for extended journeys. This sounds like science fiction because, at present, it is science fiction, lacking supporting evidence. However, the 4-hour pulse combined with the sun-war jet and the nickel-dominated chemistry adds another anomaly to the growing list. There is one further angle to consider. If metal carbonyl compounds are involved in the outgassing, and if their formation or breakdown follows a cyclic chemical process, this could introduce periodicity. Imagine a feedback loop where heating drives sublimation. Sublimation cools the surface. Cooling allows carbonyls to recondense, and the cycle repeats. This is thermodynamically plausible if the right conditions are present, but again, it requires very specific chemistry and remarkably stable conditions across the entire nucleus. It is not the first explanation one would typically consider, but it is not impossible. The 4-hour pulse is significant because it represents another data point that does not comfortably align with standard models. Considered in isolation, it is intriguing but explainable. When considered alongside everything else, it amplifies the sense that 3i Atlas operates under different rules, and we are on the verge of discovering whether those rules apply solely to this object or indicate a broader class of interstellar visitors that we have only just begun to comprehend. Because here lies the urgent reality. We will not have the luxury of studying this object leisurely over decades. We have one opportunity, a narrow window to gather close-up data from spacecraft that happen to be in the right place at the right time. That window is opening now, and within days, instruments aboard 2 missions will sweep through nearby space with their sensors directed at this enigma. What they find, or fail to find, will shape our interpretations for years to come. Part 5. The clock is ticking. This may be our sole chance to observe it up close. In the vast emptiness of space, encounters between human-made spacecraft and celestial objects are rare. They are precious opportunities orchestrated by decades of planning or seized through fortunate timing. 3i Atlas arrived in our solar system unannounced, following an orbit we did not anticipate, becoming visible only after it rounded the sun and began its outward journey. We cannot dispatch a mission to rendezvous with it. There is insufficient time to design, construct, and launch a probe that could catch up to an object already accelerating back toward interstellar space. However, through a stroke of cosmic serendipity, two spacecraft, launched for entirely different purposes, will pass within detectable range during the critical period when the comet remains observable. The European Space Agency's Hera mission, designed to study the aftermath of NASA's DART impact on the asteroid Didymos, has a flyby window between October 25th and November 1st, 2025. During this period, Hera will pass within approximately 8 million kilometers of 3I Atlas. While not close by spacecraft standards, not a true flyby in the sense of skimming past at a very short distance, it is sufficiently close for certain instruments to gather valuable data. Hera is equipped with cameras, spectrometers, and particle detectors intended for studying asteroid surfaces and dust environments. These same instruments can be retargeted, at least partially, to observe the comet's coma and tail structure. NASA's Europa Clipper, en route to Jupiter's ice-covered moon, has a similar opportunity between October 30th and November 6th. Again, we are discussing millions of kilometers, not hundreds or thousands. Europa Clipper will not resolve the nucleus. It will not capture close-up images revealing surface details, but its spectrometers can analyze the light passing through the coma. Its plasma instruments can detect charged particles stripped from the comet by the solar wind. Its magnetometers might detect signatures of magnetic draping, where the interplanetary magnetic field bends around the comet's ionized gas cloud. What makes these flybys particularly valuable is the diversity of measurements they can provide. Optical imaging from Earth captures the large-scale structure, the jets and coma, but struggles to differentiate between various chemical species or measure the physical properties of dust grains. Spectroscopy from ground-based telescopes offers compositional information, but with limitations imposed by Earth's atmosphere and the comet's brightness. Spacecraft instruments, even from considerable distances, can access wavelengths blocked by our atmosphere, measure particles directly, and observe without the blurring and scattering that plague ground-based observations. If either Hera or Europa Clipper detects strong nickel emission, this would independently confirm the spectroscopic oddity observed from Earth. If they map the coma's structure and find asymmetries consistent with the sunward jet, this strengthens the argument for a real physical feature rather than a processing artifact. If plasma detectors identify unusual ion compositions or unexpected particle populations, this could suggest exotic chemistry or even non-natural materials outgassing from the nucleus. Conversely, if the spacecraft observed nothing unusual, if their data reveals a comet that appears chemically and physically normal, then we would need to reconsider whether the ground-based anomalies represent misinterpretations or measurement errors. There is a predicted opportunity that particularly excites plasma physicists. The comet's ion tail, that stream of charged particles shed by the solar wind, will intersect the path of one or both spacecraft. When this occurs, instruments designed to measure the local space environment will suddenly find themselves immersed in comet-derived plasma. They will detect ions of whatever molecules are being ionized in the coma, including water ions, carbon monoxide ions, carbon dioxide ions, and yes, metal ions like nickel and iron if present in sufficient quantities. The mass spectrometers aboard these missions can distinguish between different ions based on their mass-to-charge ratios, providing us with a direct measurement of what is actually present in the tail, not merely what we infer from spectroscopy. Magnetic field measurements offer another diagnostic tool. When the solar wind encounters a comet, the interplanetary magnetic field becomes draped around the obstacle, creating a characteristic pattern. The shape and strength of this draping depend on the comet's outgassing rate, the composition of its coma, and the efficiency with which ions are generated and interact with the field. Deviations from the expected pattern could indicate unusual plasma physics or unexpected conductivity, which in turn might point to exotic chemistry or material properties. However, let us be realistic about the limitations. These spacecraft are not undertaking dedicated comet flybys. They are operating under tight schedules with primary mission objectives that do not involve 3I Atlas. Hera needs to reach Didymos and conduct its survey. Europa Clipper must conserve power and momentum for its arrival at Jupiter. Directing instruments at the comet requires fuel for attitude adjustments, competes with other observations, and risks compromising planned activities. The distances involved mean that resolution will be limited. We will not obtain detailed surface maps or close-up views of active vents. We will acquire contextual data, hints about composition, and environmental measurements. There is also the challenge of timing. The flybys occur over spans of several days, and the comet is in motion, changing, potentially varying in activity due to that 4-hour pulse or other factors. Coordinating observations, ensuring instruments are accurately pointed, and capturing data at optimal moments necessitate meticulous planning and a degree of luck. Mission planners are doing their utmost, but they are working within constraints and uncertainties. Historically, opportunities of this nature have been a mixed bag. When Oumuamua, the first confirmed interstellar object, traversed our solar system in 2017, we had no spacecraft positioned to observe it closely. Everything we learned came from telescopes on Earth and in Earth orbit, and it was insufficient to definitively resolve debates about its nature. By the time we recognized its strangeness, it had already passed perihelion and was fading from view. We did not get a second chance. Comet Borisov, the second confirmed interstellar visitor, arrived in 2019 and provided us with more time for study. However, again, there were no spacecraft encounters, only remote observations. 3I Atlas represents our third confirmed interstellar object, and for the first time, we have spacecraft close enough to potentially contribute in situ measurements to complement remote observations. It is not the comprehensive mission we would design if we had years to prepare, but it is infinitely better than nothing. What Hera and Europa Clipper detect or fail to detect will be cited in scientific papers for years. It will inform models, settle or intensify debates, and guide our interpretation of future interstellar visitors. The coming days will reveal whether the anomalies are robust and reproducible across different measurement techniques. If the spacecraft data aligns with the ground-based oddities, confidence in the reality of those oddities will skyrocket. If the spacecraft data contradicts or fails to observe what telescopes have reported, then we will face a calibration problem or a modeling issue to resolve. Either outcome is scientifically valuable. Either outcome moves us closer to understanding what 3I Atlas truly is. But while we await those flyby results, there is more to the story than just this single object. The anomalies do not cease with the sunward jet, the nickel chemistry, or the rhythmic pulse. When one begins to catalog everything unusual about 3I Atlas, when one compiles all observations that do not quite fit, it becomes apparent that this object is an embarrassment of riches for anomaly hunters. It is not merely one or two oddities. It is 15, perhaps more. Each demands an explanation, and each adds weight to the growing conviction that we are missing something fundamental. Part 6, 15 Anomalies and Counting. Let us assemble the dossier. Imagine we are constructing a forensic file, compiling every piece of evidence that makes 3I Atlas unusual compared to our expectations for a typical comet. Some of these anomalies might have natural explanations when considered individually. Some might be observational quirks or measurement uncertainties, but taken collectively, they paint a picture of an object that refuses to conform to our models. Anomaly 1 is the absence of a long, sweeping tail. Most comets, particularly when active and relatively close to the Sun, sport prominent tails stretching for millions of kilometers. Dust tails curve gently, following the comet's orbit. Ion tails stream directly backward, propelled by the solar wind. 3 Atlas possesses a coma, yes, but its tail structures are subdued, shorter, and less dramatic than one would predict based on its brightness and level of activity. It is as if the material ejected from the nucleus is not efficiently swept into a tail, or the production rate is lower than the coma's brightness suggests. Anomaly 2 is the sunward jet, which we have already discussed in detail. Material streaming toward the Sun, defying radiation pressure and solar wind, represents a fundamental departure from standard cometary behavior. This anomaly alone would make the object noteworthy. Anomaly 3 is the high nickel-to-low iron ratio, also covered previously. Extreme abundance ratios of metals do not align with solar or interstellar compositional norms without invoking unusual formation environments or peculiar chemistry. Anomaly 4 is the carbon dioxide-dominated coma. Most comets are rich in water. 3I Atlas reverses this trend, with CO2 outweighing water by a factor of 8. This suggests formation in a cold, carbon-rich environment, possibly around a different type of star or within a molecular cloud possessing chemistry distinct from that of our solar system's birthplace. Anomaly 5 is the suppressed water relative to carbon dioxide. This is not merely a restatement of Anomaly 4. It highlights that water, typically the dominant ice in comets, appears unusually depleted or sequestered within this object. This has implications for where and how it formed, as well as its thermal history. Anomaly 6 is the rhythmic periodic outbursts, the 4-hour and possibly 2-hour cycles we have discussed. Regular activity patterns suggest organized internal structure or specific geometric effects tied to rotation. Anomaly 7 is the asymmetric coma. Cometary comas are often asymmetric to some degree, but 3I Atlas exhibits pronounced asymmetries that do not align neatly with expected models of dust and gas distribution. The sunward jet contributes to this, but even accounting for it, the overall coma shape is peculiar. Anomaly 8 involves non-random orientation changes. Some observers reported that the direction of plumes or jets shifted over time in ways that did not clearly correlate with orbital mechanics or expected rotational effects. This is a more subtle anomaly, harder to pinpoint, but it adds to the perception that the object's activity is not following a simple pattern. Anomaly 9 is the extreme negative polarization signature. Polarimetry measures how light from an object is polarized, and comets typically exhibit certain polarization characteristics based on their dust properties. 3I Atlas displayed a deep negative polarization branch, meaning that at certain scattering angles, the light was polarized in a direction opposite to what is typical. This suggests unusual dust grain properties, perhaps a different size distribution, composition, or shape compared to solar system comets. Anomaly 10 is the anti-tail or narrow jet extension toward the Sun observed in earlier Hubble images. Prior to the striking TD image, Hubble captured hints of a narrow structure pointing sunward. At the time, it might have been dismissed as noise or a faint dust trail. In retrospect, it appears as an early indicator of Anomaly 2. Anomaly 11 is the early outgassing of water and hydroxyl far from the Sun. Observers detected water and OH emissions when the comet was still several astronomical units away, farther than significant water ice sublimation would typically be expected. This vigorous early activity suggests either that the surface ice is unusually exposed and volatile rich, or that some heat source beyond simple solar irradiation is driving sublimation. Anomaly 12 is the green color shift during a lunar eclipse. Comets can appear greenish due to emission from carbon-bearing molecules like C2, but 3I Atlas exhibited a green hue even though spectroscopy indicated a low C2 abundance. The color shift occurred during a lunar eclipse when Earth's shadow affected the comet's illumination geometry, suggesting that something about its scattering or emission properties changed in unexpected ways. Anomaly 13 is the detection of hydrogen cyanide emission. HCN was detected at a heliocentric distance of approximately 2.13 astronomical units. Interestingly, the HCN to CN ratio was similar to that of solar system comets, suggesting that at least some chemistry is normal. However, the presence of cyanide compounds adds another layer to the already complex chemical inventory, especially when considering how nickel cyanide chemistry is employed in industrial processes on Earth. Anomaly 14 is the rapid change in the nickel-to-iron ratio with heliocentric distance. Iron emission appeared only when the comet crossed inside approximately 2.64 astronomical units from the Sun. Before this threshold, nickel predominated without significant iron. After crossing it, iron became detectable. This temperature-sensitive emission profile hints at a stratified makeup or separate stores of vaporizable material that transition to gas at differing temperature points. However, the abruptness of the change is uncommon. Anomaly 15 pertains to the deferred or withheld dissemination of visual data originating from Mars orbit. The craft known as 3I Atlas navigated a relatively close trajectory to Mars, approximately 29 million kilometers distant, around the 3rd of October. Spacecraft equipped with imaging systems, such as the ExoMars Trace Gas Orbiter and Mars Express, possess the capacity to capture visual information of the comet. Nevertheless, the public disclosure of such imagery has been notably sluggish or entirely absent. The high-resolution imaging science experiment, HiRISE, situated aboard NASA's Mars Reconnaissance Orbiter, could have also rendered images of the comet. This delay might be attributed solely to administrative procedures, the temporal demands of data processing, or mission priorities. Yet, it amplifies the aura of enigma, fostering the impression that perhaps certain elements within those captured images are undergoing meticulous examination prior to their release. Each of these peculiar occurrences, when examined in isolation, could potentially be rationalized. Unusual physical properties of the dust, an exceptionally rare Genesis environment, observational misinterpretations, or delays in data handling. Nevertheless, when 15 such anomalies are aggregated, when a recurring pattern emerges that defies conventional understanding, one is compelled to question whether the established model for comets is simply insufficient for entities originating from beyond our solar system. It is conceivable that celestial bodies formed around other stars, exposed to distinct radiation environments, and comprised of ices and dust with unique primordial chemical compositions, exhibit fundamentally different behaviors. It may be the case that the principles we have deduced from studying comets born within our own solar system do not apply straightforwardly to wanderers from across the vast expanse of the galaxy. Or perhaps, just perhaps, we are observing something that does not entirely conform to natural processes. This sentiment exists as an unspoken undercurrent, a speculative notion that individuals hesitate to voice too overtly, as it risks being perceived as fringe speculation or fodder for sensationalist reporting. However, this underlying doubt persists because the accumulating data continues to present itself in ways that are unsettling. The presence of nickel unaccompanied by iron, the detection of cyanide compounds, observed rhythmic pulsing, and sunward-directed jets. It is not that any single one of these observations definitively points to an artificial origin. Rather, it is their collective presentation that forms a constellation of anomalies, prompting a re-evaluation of our fundamental assumptions. Therefore, let us directly explore this line of reasoning, not as a definitive conclusion, but as a mental exercise. What if a component of the three-eye atlas, be it a surface coating, a structural element, or a deliberately placed payload, involved manufactured materials? What would we anticipate observing, and does it align with our current findings? Part 7. The Engineered Alloy Hypothesis. One of the most unconventional suppositions circulating in the periphery of scientific discourse is the following. Certain portions of the three-eye atlas might be artificially constructed, not necessarily the entirety of the object. It is possible that only a shell, a stratum, or a component embedded within or affixed to what is otherwise a naturally occurring cometary nucleus. This concept sounds akin to science fiction, and it likely is. However, let us follow the logical progression to ascertain its implications. Human technology extensively employs nickel alloys. Stainless steel, the pervasive metal resistant to corrosion found in applications ranging from domestic sinks to components of spacecraft, incorporates both chromium and nickel. Superalloys, utilized in jet engines and rocket nozzles, are materials engineered to withstand extreme temperatures and corrosive conditions, and these are frequently nickel-based. Examples include Inconel and Hastelloy, which are proprietary designations for nickel alloys valued for their exceptional strength and resilience. If an advanced civilization were to construct a probe or an instrument package designed to endure millennia adrift in interstellar space, exposed to cosmic radiation, micrometeorite impacts, and the corrosive effects of trace gases, nickel alloys would represent a logical material selection. The chemistry of nickel cyanide is employed in electroplating, a process wherein a thin layer of nickel is deposited onto another metallic surface for purposes of protection or aesthetic enhancement. This chemical process involves cyanide ions, which bond with nickel and assist in regulating the deposition procedure. If one were to coat a structure with nickel to enhance its durability, one would be working with nickel cyanide solutions. Over extended periods, particularly under the harsh conditions of space, such coatings could deteriorate. Ultraviolet radiation, cycles of temperature fluctuation, and abrasion from micrometeorites could all contribute to the gradual erosion of a nickel-rich surface layer. As this layer degrades, it would release nickel atoms and potentially cyanide compounds into the surrounding vacuum. Now, envision this hypothetical nickel-plated structure embedded within or attached to a cometary nucleus. As the comet approaches the sun and experiences heating, the surrounding ice vaporizes, releasing gases and fine particles. The structure, if partially exposed, also undergoes heating. Any remaining volatile compounds, any degraded surface materials, would commence to outgas. One would then expect emissions of nickel, possibly cyanide species, and, contingent upon the precise chemical interactions, various carbon-containing molecules. The relative proportions would not conform to those expected from natural cometary material, as one would be observing not merely sublimated ice, but the decomposition products of manufactured materials intermingled with the natural effusions. This scenario could account for the elevated nickel-to-iron ratio if the manufactured component utilized a nickel-rich alloy with minimal iron content. It could explain the detected hydrogen cyanide compounds if cyanide chemistry played a role in the material's fabrication or surface treatment. It might even explain the dominance of carbon dioxide if the structure incorporated carbon-based elements, such as polymers or organic coatings, which break down into CO2 when subjected to ultraviolet irradiation and elevated temperatures. The observed rhythmic 4-hour periodicity might also be more comprehensible within this framework. If the engineered component features apertures, valves, or structural elements designed to regulate gas flow, either intentionally or as a consequence of its degradation process, periodic releases could occur. Imagine a contained volume that accumulates sublimated gas from the surrounding ice, builds internal pressure, and then expels it through a fissure or opening. Once discharged, the pressure within the compartment would diminish, initiating the refilling process, thus repeating the cycle. A duration of 4 hours would represent the characteristic time frame for this specific system, determined by the dimensions of the compartment, the rate of sublimation, and the resistance to flow through the vent. The sunward jet becomes less enigmatic if it is propelled by something other than random sublimation. Consider the possibility that the engineered structure possesses a directional aperture, a nozzle, or an opening that, by chance, points towards the sun due to the object's rotational orientation or tumbling motion. Gas expelled through such an aperture would generate a jet in that particular direction, irrespective of the sun's position. This would not be a consequence of combating radiation pressure so much as bypassing conventional mechanisms by expelling material from a specific point with sufficient force to locally counteract solar wind effects. While this entire explanation sounds disturbingly plausible, once one begins to explore it, we must approach it with absolute candor regarding its inherent requirements. It necessitates the existence of an advanced civilization that constructed a probe or object. It assumes this object subsequently entered interstellar space. It further postulates that this object fortuitously passed through our solar system. And critically, it implies that this object has undergone sufficient degradation to release detectable signatures without overtly betraying its artificial nature. This constitutes a substantial number of coincidences. Moreover, it requires that we are misinterpreting or overlooking natural phenomena that could account for these same observations. The scientific community has a specific term for this kind of conjecture: the principle that extraordinary claims necessitate extraordinary evidence, a tenet often credited to Carl Sagan. The underlying concept is straightforward. The more unusual and paradigm-altering a proposition, the greater the burden of proof required to substantiate it. Asserting that the three-eye atlas exhibits unusual chemical properties is a relatively minor claim, demanding only moderate corroboration. Proposing that it is partially artificial, however, is an extraordinary claim, requiring substantial and compelling evidence. Do we possess this level of evidence at present? No. What we have are intriguing anomalies, suggestive patterns, and a deficit of fully satisfactory, naturalistic explanations. This is distinct from definitive proof of artificiality. Natural processes can frequently surprise us. The universe is remarkably inventive. Chemical reactions under extreme and unusual conditions can yield unexpected outcomes. Interstellar environments are not extensively documented. We have conducted thorough investigations of comets within our solar system, but all of these comets originated from the same primordial disk, composed of identical starting materials and formed under analogous conditions. A comet originating from interstellar space, formed around a different star within a molecular cloud, possessing a different metallicity and irradiated by a distinct stellar spectrum, might simply exhibit peculiarities without being artificial in nature. Such an object could reveal that the diversity of cometary chemistry is far greater than we currently understand. However, we should not entirely dismiss this speculative possibility. Scientific progress is driven by the consideration of potential explanations, their subsequent rigorous testing, and either their confirmation or refutation. The engineered alloy hypothesis is, at least in principle, subject to empirical verification. If spacecraft flybys detect particles or ions exhibiting isotopic ratios inconsistent with natural nucleosynthesis, this would serve as decisive evidence. Should imaging reveal geometric configurations, straight edges, or regular patterns not typically observed in natural accumulations of debris, this would be highly persuasive. If spectroscopic analysis uncovers molecules that are exclusively produced through industrial processes and lack any plausible natural formation pathway, we would be compelled to seriously consider this proposition. Conversely, if subsequent observations identify natural mechanisms that adequately explain the nickel predominance, the excess carbon dioxide, and the sunward jet without recourse to engineered materials, then the hypothesis would be rendered obsolete by Occam's razor, wherein the simpler explanation prevails. We have not yet reached that definitive stage. We currently reside in an uncomfortable transitional phase, where the data is sufficiently unusual to provoke contemplation, yet not conclusive enough to establish a firm conclusion. What renders this particular juncture exceptionally captivating is that our speculation is not occurring in isolation. We stand on the precipice of acquiring new empirical data. The outcomes of the upcoming flybys will either fortify or diminish the plausibility of unconventional explanations. However, even as we await this data, another dimension to this narrative exists, another perspective that deepens the enigma. At times, what remains unseen carries as much significance as what is observed. And in the instance of the Third Atlas, there are missing elements, withheld imagery, and inexplicable delays that introduce an unsettling layer of intrigue. Part 8. Suppressed data and the silence from Mars orbiters. On occasion, what is concealed communicates as powerfully as what is revealed. In an era characterized by instantaneous dissemination of information, where astronomical discoveries are broadcast via social media within mere hours, and preprint servers are inundated with novel research papers, the absence of anticipated data itself becomes a discernible signal. The 3I Atlas passed relatively close to Mars during the early days of October, proximate enough that numerous Mars orbiters should have had excellent vantage points for observing the comet. Nevertheless, the public disclosure of imagery from these orbiters has been conspicuously delayed and, in certain instances, seemingly non-existent. The ExoMars Trace Gas Orbiter, an undertaking by the European Space Agency dedicated to the study of the Martian atmosphere, is equipped with cameras capable of capturing images of objects in space. Mars Express, another orbiter operated by the ESA, which has been circling Mars since the year 2003, also possesses imaging capabilities. NASA's Mars Reconnaissance Orbiter carries the HiRISE instrument, a camera so advanced that it can discern features on the Martian surface, measuring less than 1 meter in dimension. When directed towards a comet situated millions of kilometers away, HiRISE would not achieve resolution at the surface level, but it could undoubtedly capture the structure of the coma, the characteristics of its jets, and its overall morphology with considerably greater clarity than most terrestrial telescopes. The Third Atlas reached its closest point to Mars approximately on the 3rd of October, at a distance of roughly 29 million kilometers. While this does not constitute an extremely close passage, it falls well within the imaging range of spacecraft instruments. The opportunity was present. The pertinent question is whether those instruments were indeed directed towards the comet. And if they were, why have we not witnessed the results? There exist entirely prosaic explanations for delayed data releases. Data transmitted from spacecraft undergoes processing. Raw images require calibration, correction for instrumental anomalies, and validation before being disseminated to the public or even to the broader scientific community. Mission teams operate under specific priorities. The primary objective of Mars orbiters is the study of Mars itself, not the opportunistic observation of comets. Diverting resources from core mission objectives to image a passing comet necessitates clear justification, meticulous scheduling, and often negotiation between various scientific teams. It is plausible that these observations were assigned a low priority, undertaken only if circumstances permitted, but not deemed essential. Consequently, the data may simply not have been processed yet, as other tasks took precedence. Furthermore, there is the practical consideration of observational geometry. The mere fact that a comet passes in proximity to Mars does not guarantee that orbiters in Martian orbit can readily acquire imagery of it. Orbital mechanics, communication windows with Earth, and constraints on spacecraft orientation collectively limit the feasible observational possibilities. It is possible that the Mars orbiters were not positioned advantageously or were not configured to effectively observe the comet. Perhaps they attempted to do so but encountered technical difficulties or unfavorable environmental conditions. While not weather in the terrestrial sense, dust storms on Mars can impede surface-based observations, although they would not impact orbital cameras. However, let us consider the less conventional possibilities. What if the images do exist, have been processed, and are being withheld pending further analysis? What if something within those images is sufficiently anomalous to prompt mission teams to meticulously reevaluate their interpretations before disseminating data that could be perceived as controversial? Space agencies are inherently cautious entities. They have experienced situations in the past where the premature release of data led to subsequent reinterpretations or corrections, resulting in public embarrassment and a diminished level of trust. If High-Rise or the TGO captured something unexpected within the inner coma of 32nd Atlas, something that deviates from established models, the natural inclination would be to conduct thorough verification before making it public. There is a historical precedent for such prudence. When unusual features are detected, when anomalies emerge that might challenge established scientific paradigms or generate sensational headlines, the data undergoes heightened scrutiny. Review committees are convened. Alternative explanations are exhaustively investigated. Only when the team is confident in its understanding of what is being observed, or confident that they have explored all plausible prosaic explanations without success, is the data released. This process can extend over months or even years. The delay could also stem from political or administrative considerations rather than purely scientific ones. Space agencies are governmental or intergovernmental bodies subject to public relations imperatives, funding pressures, and international collaborative agreements. If data from one mission has implications for the interpretation of another mission or touches upon sensitive subjects, there might be delays in coordination while various stakeholders synchronize their communications. This may sound cynical, and perhaps it is, but these organizations do not operate in isolation. They navigate complex environments involving public perception, scientific integrity, and institutional interests. Some observers have suggested, perhaps unfairly, that if the Mars orbiter images revealed unequivocal evidence of artificial construction or undeniable anomalies that would necessitate a reassessment of the nature of 32nd Atlas, such images might be deliberately withheld. The underlying rationale is that extraordinary assertions require extraordinary prudence, and prematurely releasing such images could precipitate a wave of media sensationalism, public confusion, and pressure on scientists to provide answers they have not yet formulated. It would be preferable to withhold such information until a more complete picture emerges, until multiple lines of evidence converge and a coherent narrative can be presented. This line of speculation rapidly enters the realm of conspiracy theories, and we must exercise caution to avoid venturing into such territory without supporting evidence. There is no indication of a coordinated effort to conceal information. No leaked internal communication or whistleblower has emerged to suggest that something astonishing is being deliberately hidden. What we are observing is the absence of anticipated data, coupled with the natural human inclination to fill informational gaps with conjecture. This absence might signify nothing, or it might signify everything. We do not yet possess the certainty to determine. What exacerbates the frustration regarding this absence is that the imagery from the Mars orbiters has the potential to resolve key questions. If these images depict a perfectly ordinary coma, devoid of a sun-war jet or any unusual features, it would cast doubt upon the observations made from Earth-based telescopes. If, conversely, they clearly show the sun-war jet from a different perspective and with high resolution, it would confirm its existence beyond reasonable doubt. If they reveal structure within the inner coma, suggesting symmetry or concentrated expulsion of material, it would provide invaluable guidance for our theoretical models. The data presumably exists in some form. We are simply awaiting its emergence from the institutional processes. However, the lack of Mars imagery is not the sole peculiar coincidence surrounding the Thursand Atlas. In the days encompassing the comet's closest approach to the Sun and its most anomalous behavior, other unusual events were reported in the vicinity of Earth and within the solar environment. When considered collectively, these events form a pattern that could be purely coincidental, or they might hint at something more coordinated or causally interconnected occurring in our cosmic neighborhood. Part 9. Cosmic Coincidences and Sun-Diving Objects. What if the peculiarities of the Thurthara Atlas are not isolated incidents? What if they are part of a larger pattern? Between the 11th and the 14th of October 2025, reports surfaced of 4 distinct objects identified as sun grazers descending towards the Sun. These objects, tracked by solar observatories, appear to originate from approximately the same general region of the sky as the Thurtharn Atlas. They plunge towards our star, with some apparently disintegrating and others vanishing within the Sun's intense glare. Sun-grazing comets are not an infrequent phenomenon. The Kreutz family, a collection of comets believed to be fragments of a larger parent body that disintegrated centuries ago, regularly contributes members that dive sunward. Solar observatories catalog dozens of these doomed comets annually as they vaporize in the Sun's extreme heat. However, the timing of these events is noteworthy. 4 objects within a 4-day period, all originating from a similar direction, coinciding with the time frame during which the Thurthard Atlas exhibited its most unusual characteristics and approached its own perihelion. Is it coincidence? Most likely. The sky is vast, and the volume of space near the Sun is constantly traversed by smaller celestial bodies. Our enhanced observational capabilities, particularly with space-based solar telescopes, mean that we are detecting a greater number of these objects than ever before. Discovering 4 in rapid succession is not statistically improbable, nor is it particularly unlikely during periods of heightened solar activity. Nevertheless, the clustering of these events provokes contemplation. Could these sun-diving objects be associated with the 33rd Atlas? Could they be fragments that detached at an earlier stage of its trajectory, following slightly different orbital paths that converged on the Sun around the same temporal juncture? Cometary nuclei are inherently fragile. Tidal forces, thermal stresses, and rotational instability can fracture them into multiple pieces. If the 3-3 Atlas shed fragments months or years prior, those fragments might possess orbits that differ marginally from the main nucleus, leading them to reach perihelion at distinct times. We have witnessed similar occurrences with other comets. Shoemaker-Levy 9 famously fragmented prior to its collision with Jupiter, resulting in a string of impact sites that struck the planet over a period of several days. Spectroscopic analysis of the sun-diving objects could provide a means to test this hypothesis. If their composition aligns with the anomalous chemistry of the 33rd Atlas, it would strengthen the presumed connection. Conversely, if they exhibit normal cometary composition, they are likely unrelated. However, obtaining detailed spectral data from objects on the verge of being incinerated by the Sun presents significant challenges. They are faint, move at high velocities, and are visible only briefly. Most detections of sun grazers are made by coronagraphs, which use an occulting disk to block the Sun's direct light and reveal the faint surrounding corona. These images do not typically yield spectral information. Another peculiar event occurred during this time frame that captured public attention, although it is even more difficult to evaluate. During the launch of a SpaceX Starship, observers analyzing video footage of the spacecraft against the backdrop of the Moon noted a bright point of light in close proximity to the lunar disk. A peculiar point materialized, seeming to hang motionless for several moments, defying identification as any known celestial body like a satellite, star, or planet. Subsequently, it vanished. Unsurprisingly, the internet buzzed with conjectures. Was this a genuine entity, perhaps a craft, or merely space debris? Or could it be an optical illusion, a lens flare, or a reflection captured by the camera's apparatus? Lens flares are a common occurrence in astrophotography, particularly when brilliant sources such as the moon are in view. Light can refract within optical components, bounce off sensor surfaces, and generate phantom images appearing as bright specks or elongated marks. Differentiating between authentic objects and optical artifacts necessitates a meticulous examination of the original visual data, a thorough understanding of the photographic equipment employed, and ideally, corroboration from multiple, independent camera sources. In this specific instance, such rigorous analysis has either yielded inconclusive results or has not been publicly disclosed. While the luminous dot might indeed represent a tangible object, it is equally, if not more, plausible that it is a commonplace optical anomaly. The tangential relevance of this event to Three Eye Atlas stems from its temporal proximity. The Starship launch took place in the middle of October, coinciding with a period of heightened cometary activity and the appearance of sun-diving objects. If one is predisposed to seeking patterns, one might question if there exists a connection between these occurrences. Could the bright point observed near the moon be linked to the phenomena causing the cometary anomalies? Is it possible that some coordinated phenomenon, or an unobserved process, is simultaneously affecting multiple bodies within Earth's immediate vicinity? This is precisely where caution is paramount, and speculation must be tempered. Coincidences are an everyday reality. Human beings are inherently wired for pattern recognition, often perceiving connections even in their absence, a trait likely fostered by evolutionary pressures where mistaking a non-existent threat for a real one carried fewer consequences than overlooking a genuine danger. Our brains automatically construct narratives by linking disparate events, but this automatic process does not validate the existence of those connections. Nevertheless, let us briefly entertain the notion, not as a firm hypothesis, but as a mental exercise. Imagine a cosmic event or energetic pulse, a disturbance within the interplanetary medium that simultaneously impacted numerous small celestial bodies. Perhaps a surge of high-energy particles emanating from the sun, a coronal mass ejection with unusual characteristics, or a wave of increased density propagating through the interplanetary medium. Could such an event instigate outgassing in comets, alter their orbital paths, or interact with dust and debris in a manner that produces transient visual effects? While the underlying physics would present significant challenges to unravel, it is not, in principle, an impossibility. Coronal mass ejections are immense expulsions of plasma and magnetic fields from the sun that travel at considerable speeds across the solar system. Upon reaching Earth, they induce geomagnetic storms, create auroral displays, and disrupt satellite operations and power grids. When they encounter comets, they can compress their comas, intensify their ion tails, and trigger outbursts. A particularly potent or atypical CME occurring in early to mid-October could have influenced 3 Atlas and potentially other celestial bodies in interplanetary space. Solar observatories continuously monitor the sun for such events. A prompt review of solar activity reports from October would reveal whether any significant CMEs or solar flares occurred during the relevant time frame. If such an event is documented, it could offer a naturalistic explanation for some of the observed phenomena. If not, then coincidence remains the most probable cause. The sun-diving objects, the luminous point observed during the Starship launch, and the peculiar behavior of 3 Atlas might simply be unrelated occurrences that coincidentally clustered in time, or they could indeed share a common, as yet unidentified, causal factor. In the absence of more comprehensive data, we are unable to definitively distinguish between these possibilities. What can be stated with certainty is that October of the year 2025 has proven to be an exceptionally eventful month for both near-Earth and solar system astronomy, with 3I Atlas occupying a central position within this flurry of activity. It stands out as the most anomalous and intensely scrutinized object among them. However, 3 Atlas is not the inaugural visitor from beyond our solar system to challenge established scientific paradigms. It represents a step in an unfolding sequence, a procession of objects originating from outside our solar system, each deviating from expected norms in its own unique fashion. To grasp the broader context in which 3I Atlas fits, it is essential to examine its predecessors and ascertain whether a discernible pattern is emerging in the behavior of these interstellar voyagers. This leads us to Part 10, focusing on the motif of reversal exhibited by cosmic visitors. While 3 Atlas may possess unique characteristics, it might also conform to a pattern that is only now becoming apparent. This pattern involves a reversal of expectations, where objects originating from interstellar space arrive and fundamentally contradict our preconceived notions. This phenomenon commenced in October of the year 2017 with Oumuamua, the very first confirmed interstellar object detected traversing our solar system. Oumuamua presented peculiarities from its inception. It exhibited no visible coma, no tail, and no discernible signs of outgassing, despite its trajectory bringing it sufficiently close to the Sun for any embedded water ice to have sublimated intensely. Based on this apparent lack of activity, it was categorized as an asteroid. However, its trajectory presented a different narrative. As astronomers meticulously tracked Oumuamua's path, they observed a subtle acceleration away from the Sun, an effect that could not be attributed solely to gravitational forces. An external impetus was clearly influencing its motion. In the case of comets, this type of non-gravitational acceleration is a well-understood and common occurrence. The process of outgassing generates a propulsive effect analogous to a rocket. Material is expelled from the sun-facing side, and the resulting recoil subtly nudges the nucleus in the opposite direction. Yet, Oumuamua displayed no visible outgassing, no coma, no jets, no detectable gas emissions. Nevertheless, it accelerated as if such processes were active. A multitude of explanations emerged. Perhaps it was outgassing an extremely faint substance, such as hydrogen, which would not produce a visible coma but could still provide propulsion. Alternatively, it might have been subjected to an exceptionally strong radiation pressure, acting upon an object with an extremely thin, flattened shape, resembling a solar sail. Another possibility posited was that it consisted of solid hydrogen ice, an exotic and fragile substance that sublimates imperceptibly. Each proposed explanation faced significant challenges, necessitating assumptions that stretched the boundaries of conventional understanding. Furthermore, its shape posed a distinct enigma. Observational data suggested that Oumuamua was exceptionally elongated, possibly 10 times longer than it was wide, presenting a cigar-like form, or perhaps even a flat, pancake-like structure. No asteroid or comet catalogued within our solar system bore such an unusual morphology. The scientific community engaged in intense debate. The majority of researchers lean towards naturalistic explanations, however unconventional. Yet, a select few, most notably astronomer Avi Loeb from Harvard University, posited that Oumuamua's observed characteristics were consistent with an artificial origin, perhaps a light sail or a probe dispatched by an extraterrestrial civilization. This suggestion was, to put it mildly, highly controversial. Most astronomers considered it premature and inadequately substantiated by the available data. Nonetheless, the idea permeated public consciousness and proved remarkably persistent. Oumuamua transcended its status as a mere scientific puzzle, becoming a cultural touchstone for the profound question of whether humanity is alone in the universe. Subsequently, in August of the year 2019, amateur astronomer Gennady Borisov discovered two icy bodies, the second confirmed interstellar object. This particular object bore a striking resemblance to a conventional comet. It possessed a distinct coma, exhibited vigorous outgassing, and contained familiar molecular compounds, such as water and carbon monoxide, in proportions consistent with expectations. Its behavior was reassuringly conventional. Researchers suggested that interstellar visitors could, in fact, be ordinary. Borisov demonstrated that not every object originating from beyond our solar system is destined to defy established norms. It was a comet, and it behaved as a comet should. While its interstellar origin was indeed extraordinary, its fundamental nature was comfortingly familiar. However, we now have 3 Atlas, and the strangeness has returned with amplified intensity. If Oumuamua was perplexing due to what it lacked, 3 Atlas is perplexing due to what it exhibits in unexpected locations. It displays a sunward jet where an anti-solar tail would typically be found, contains nickel devoid of iron, and exhibits carbon dioxide that overshadows water. Its activity is characterized by rhythmic pulsations, reminiscent of a mechanical heartbeat. This object is not merely failing to behave like a comet, it is acting like a comet that has completely disregarded the established scientific literature. When these 3 visitors are arranged in chronological order, a distinct pattern emerges. First, an object displaying no activity where activity is expected, yet exhibiting mysterious acceleration. Second, an object with standard activity and predictable chemical composition. Third, an object demonstrating reversed activity and peculiar chemical properties. It's as if the universe is presenting us with a progressive series of anomalies, a cosmic test to gauge our response. Alternatively, it might be conveying that our classifications of comets, asteroids, and interstellar visitors are overly rigid, perhaps too narrowly defined by observations within a single solar system. The crucial question is whether these objects represent statistical outliers or heralds of a broader phenomenon. Are they rare exceptions, chance occurrences that capture our attention precisely because of their unusual nature, while countless ordinary interstellar objects pass undetected due to their faintness or unremarkable characteristics? Or do they represent the vanguard of a far more extensive population of peculiar entities drifting through the galaxy, objects formed under conditions so vastly different from those in our solar system that they inherently defy our expectations? The implications of this question are profound. If the majority of interstellar visitors are anomalous, then our solar system's comets and asteroids might themselves be the outliers, products of a specific set of formation conditions that are not representative of the galaxy at large. In such a scenario, we would need to broaden our theoretical models, incorporating a significantly wider spectrum of chemical and physical possibilities, and acknowledge that what we currently perceive as normal is merely a localized norm, not a universal constant. Conversely, if most interstellar visitors are ordinary, and our attention is merely drawn to the unusual ones because they are conspicuous, then Oumuamua and 3 Atlas are mere curiosities, interesting certainly, but not paradigm-altering discoveries. They would be the astronomical equivalent of rare birth defects or unusual circumstances that do not reflect the general population. While we would still seek to understand them, they would not necessitate a rewriting of our scientific textbooks. The reversal motif, this propensity for interstellar objects to subvert expectations, might be conveying a deeper truth about the galaxy's inherent diversity. Star formation transpires in a multitude of environments. Some stars coalesce in dense clusters, subjected to intense radiation and gravitational interactions. others form in isolation within the sparse outer reaches of molecular clouds. The elemental composition of the gas and dust varies depending on the metallicity of the region, the historical enrichment by supernova remnants, and the proximity of massive stars. Comets forming around stars in metal-rich environments might exhibit different chemical signatures compared to those originating in metal-poor regions. Comets formed in close proximity to massive stars may have been exposed to more intense radiation, potentially altering their surface characteristics or preferentially driving off certain volatile compounds. 3 Atlas, with its pronounced carbon dioxide abundance and anomalous metallic composition, could be the product of such an unusual birthplace. It might have formed around a carbon star, a stellar type characterized by a higher abundance of carbon than oxygen in its outer atmosphere, leading to the formation of carbon-rich dust and chemistry. Perhaps it resided for an extended period within a dense molecular cloud, where cosmic rays subjected its ices to unique chemical transformations. It could also be exceedingly old, perhaps billions of years old, with its surface altered by prolonged exposure to the interstellar radiation field. All of these are plausible natural explanations that could account for its peculiarities without resorting to artificiality. However, the reversal motif also lends itself to a more speculative interpretation. If interstellar space is occasionally traversed by probes or artifacts from other civilizations, these objects would inherently defy our expectations, as they would not be products of natural processes. Their constituent materials would be selected for engineering purposes rather than cosmic abundance. Their structures would be optimized for function, not random accretion. They might even possess systems that operate with rhythmic or directional regularity, having been deliberately constructed to do so. Within this framework, the observed reversal is not a coincidence but a distinctive characteristic, a signature. Objects that deviate from established norms might be doing so because they were created by entities that themselves defy natural norms. This brings us to a pivotal juncture. 3 Atlas, Oumuamua, and potentially future interstellar visitors are compelling us to expand our conceptual horizons. Whether the explanation lies in exotic natural phenomena or something more radical, we are being compelled to confront the limitations of our existing models. As we grapple with these cosmic enigmas, it is noteworthy that the year 2025 has been a period of paradigm-challenging discoveries across multiple scientific disciplines. The emergence of 3 Atlas is not occurring in isolation. It is happening during a year when other fundamental assumptions are undergoing rigorous scrutiny. Dark stars are confounding cosmologists. Artificial intelligence is uncovering patterns in physics that eluded human researchers. Quantum teleportation is achieving milestones once deemed impossible, and fusion energy is surpassing critical thresholds, promising to revolutionize civilization. It is conceivable that we are entering an era where anomalies are becoming the norm, where the universe is revealing complexities we had not anticipated across all scales of study. Part 11 delves into the dark stars debate. Recent findings from the James Webb Space Telescope and other astronomical surveys have ignited an unexpected debate within cosmology concerning the formation sequence of the universe's earliest structures. The prevailing standard model posits that galaxies formed first, evolving from minor density fluctuations in the nascent universe, and subsequently supermassive black holes emerged at their centers as matter accumulated and collapsed. This sequence seemed logical. Gas condenses to form stars, stars aggregate into galaxies, and eventually, sufficient mass concentrates in galactic cores to give rise to supermassive black holes. This represents a bottom-up process, building complexity from rudimentary beginnings. However, the James Webb Space Telescope, JWST, consistently detects black holes that appear disproportionately large and formed too early. These are supermassive black holes, possessing masses millions to billions of times that of our Sun, existing at a time when the universe was less than 1 billion years old. This time frame is insufficient for them to have grown to such magnitudes through the conventional processes of accretion and mergers. This implies one of two possibilities. Either these black holes originated with significantly greater masses than current theories predict, or they underwent exceptionally rapid growth, or the entire formation sequence is fundamentally incorrect. An alternative hypothesis suggests that black holes may have formed prior to galaxies, acting as seeds for the structures that would later evolve into galactic centers. This concept has given rise to the notion of dark stars, hypothetical early celestial objects powered not by nuclear fusion, as is the case with conventional stars, but by the annihilation of dark matter particles. If dark matter accumulated in dense concentrations in the early universe and began to annihilate, it could release energy, heating surrounding gas and causing it to emit radiation. These dark stars could be immense, far exceeding the size of any fusion-powered star, and could eventually collapse to form black holes, which would then serve as the nuclei for subsequent galaxy formation. This scenario represents a reversal of the expected order: black holes preceding galaxies, rather than galaxies preceding black holes. The empirical evidence remains inconclusive. The observations fueling this debate are at the very limits of JWST's observational capabilities, and alternative explanations are still being considered. Perhaps the black holes are not as massive as they appear. It is also possible that they are accreting matter at rates exceeding current theoretical estimates. Furthermore, our models of early universe conditions might require refinement. However, the mere fact that this discussion is taking place and that the established cosmological sequence is being questioned based on concrete observational data reflects a broader trend. Our theoretical frameworks are being rigorously tested and found wanting. The universe is proving to be more intricate and astonishing than our neatly constructed models had anticipated. If we can err on something as fundamental as the formation sequence of galaxies and black holes, structures that define the large-scale architecture of the cosmos, then making errors regarding the behavior of interstellar comets seems almost insignificant in comparison. In both instances, the issue involves extrapolating from limited observations and assuming universal applicability, only to discover that the universe harbors complexities we had not accounted for. The dark stars debate is relevant to our discussion of 3 Atlas because it establishes a crucial context. We are not currently in a period of scientific certainty where all major questions have been resolved, and we are merely refining details. Instead, we are in an era where fundamental assumptions are being challenged across a multitude of scientific domains. This does not imply that every anomaly represents a revolutionary breakthrough. Most anomalies ultimately resolve into measurement errors, calibration issues, or previously understood phenomena appearing in unfamiliar guises. However, some anomalies are indeed genuine, and a subset of these real anomalies necessitates the rebuilding of our theories from the ground up. 3 Atlas might be one of these theory-shattering anomalies, or it could simply be a lesson in exotic yet naturally occurring cosmic chemistry. The essential point is that we cannot dismiss it solely because it fails to align with our current models, especially when those models are demonstrably incomplete. The universe is under no obligation to conform to our expectations, and the year 2025 is repeatedly reinforcing that lesson. Part 12 explores the intersection of AI and physics. In the year 2025, artificial intelligence has transcended its role as a mere assistant to scientists. It is now actively uncovering discoveries that have eluded human researchers. Machine learning algorithms, trained on extensive datasets, are adept at identifying patterns, correlations, and anomalies that would require human researchers years to detect if they could do so at all. This capability is profoundly transforming every field it touches, and astrophysics is no exception. Recent scholarly articles in high-energy physics and cosmology have listed AI systems as co-authors, acknowledging the substantial contributions of these algorithms to the discovery process. These are not simply tools for data processing. They function as hypothesis generators and pattern recognizers, operating within high-dimensional spaces where human intuition often struggles. An AI system trained on galactic spectra, for instance, can simultaneously identify unusual emission lines across thousands of celestial objects. Similarly, an AI analyzing the light curves of variable stars can detect periodicities buried within noise that would be missed by visual inspection. This advanced capability holds immense significance for the study of objects like 3 Atlas. The data we possess, including spectral information, imagery, and light curves, contains far more information than any single human researcher can fully extract. There exist subtle correlations between chemical abundances and patterns of activity, intricate timing relationships, and spatial structures within the coma that could potentially reveal internal organization. An AI specifically trained on cometary data and subsequently applied to 3 Atlas might identify patterns that elucidate its anomalies or flag additional peculiarities that have gone unnoticed. However, this powerful capability is not without its risks. AI systems are susceptible to hallucinating patterns within noise. They can become overly specialized to their training data, learning the idiosyncrasies of specific instruments rather than genuine physical relationships. Furthermore, they can internalize biases present in their training sets, inadvertently reinforcing existing assumptions rather than challenging them. An AI primarily trained on comets within our solar system, for example, might classify virtually every characteristic of 3 Atlas as anomalous simply because it deviates from the familiar rather than due to any inherent physical impossibility. The crucial element lies in integrating the AI's pattern recognition prowess with human skepticism and physical intuition. The AI should be utilized to scan for anomalies, but human experts must be responsible for verifying these findings, meticulously checking for instrumental artifacts, and constructing physical models to provide explanations. This hybrid approach is already being successfully implemented in the field of gravitational wave astronomy, where AI identifies potential signals within detector noise, and human experts then evaluate whether they represent genuine events or mere glitches. The same methodology holds the potential to revolutionize our approach to studying interstellar visitors. Envision an AI system that meticulously processes every observation of 3I Atlas, all spectra, images, and timing measurements, and systematically searches for interrelationships. It might discover that the observed 4-hour pulsation correlates with specific spectral line intensities, suggesting a cyclical chemical process. It might determine that the intensity of the sunward jet fluctuates in conjunction with the nickel-to-iron ratio, hinting at a shared underlying mechanism. It could even identify precursor signals, subtle shifts in the coma occurring hours before significant outbursts, potentially enabling the prediction of future activity. It's possible that no patterns will be found, which would confirm that the anomalies are indeed random or are caused by processes too intricate or chaotic for pattern recognition. Such a conclusion would also be significant. It would indicate that we aren't overlooking straightforward connections and that the mystery is genuinely perplexing. The overarching idea is that the year 2025 marks a turning point in our scientific methodologies. We are enhancing human intellect with artificial intelligence in ways that are fundamentally different from prior computational tools. This advancement broadens the scope of what's achievable, the kinds of questions we can pose, and the speed at which we can find answers. If there are secrets hidden within the data of Third Atlas, AI might hold the key to uncovering them. Furthermore, if AI substantiates the existence of robust and interconnected anomalies, it would considerably strengthen the arguments for unconventional explanations, whether natural or otherwise. Part 13. The Quantum Teleportation Breakthrough. Information doesn't traverse space. It ceases to exist in one location and reappears in another without bridging the intervening distance. While this sounds like sorcery, by 2025, it's becoming a standard practice. Researchers have recently accomplished something that would have seemed inconceivable a decade prior. They have successfully teleported quantum information across 56 kilometers of conventional fiber optic cable, integrated alongside regular internet traffic, the very same cables that carry your emails and video streams. This is not a hypothetical scenario. It has happened. The advancement originated from scientists at Northwestern University, collaborating with teams from various institutions. Their findings demonstrated that quantum states could be transferred with over 90% accuracy over metropolitan distances, utilizing equipment compatible with existing infrastructure. Consider this for a moment. The same fiber optic cables that deliver Netflix to your home, the same conduits buried beneath city streets that transmit financial transactions and medical records, are now carrying quantum information. The very fabric of reality, in its most fundamental form, is being transmitted alongside your daily news. The underlying mechanism operates on principles that should unsettle anyone who believes space is merely an empty vacuum. Quantum entanglement establishes a linkage between two particles, a connection so instantaneous that Einstein himself described it as spooky action at a distance. Two particles become entangled, their properties permanently intertwined. When you measure one, the other instantaneously responds, irrespective of the distance separating them, whether it's kilometers or light years. The physicists involved in this research meticulously prepare pairs of entangled photons. One photon carries the quantum state intended for transfer, while the other awaits at the destination. The instant a measurement is performed on the first photon and an intermediary particle, that measurement compels the distant photon to collapse into the original state, meaning the information is no longer here. It now exists there. No signal travels between them. No message passes through space. The correlation is immediate. Einstein found this deeply unsettling, calling it ghostly and unacceptable, a violation of fundamental physics principles. Yet, here we are in 2025, harnessing this very ghostliness. But here's the crucial part for understanding the implications. This process demands such precise timing that error correction becomes an intricate challenge. Each entangled photon journeys through fiber optic cable, and fiber optic cable is inherently detrimental to delicate quantum states. Thermal noise, vibrations, and electromagnetic interference all threaten to decohere the quantum information before it reaches its destination. The researchers have devised a solution using advanced filtering techniques, superconducting detectors cooled to temperatures just above absolute zero, and active feed-forward protocols where classical information pertaining to measurement results travels alongside the quantum signal. This classical information informs the receiver how to manipulate the quantum state to restore it perfectly. It's akin to simultaneously sending a message and the key to its decryption, except the key itself is quantum and requires extraordinary protection. The distances involved, while not vast by cosmic standards, are significant for quantum systems. 56 kilometers is a considerable expanse to maintain quantum coherence. The fact that this is now replicable, achievable repeatedly with consistent outcomes, signifies a transition from a laboratory curiosity to a practical technology. The implications for deep space communication are staggering. Imagine probes exploring the outer solar system, or, eventually, interstellar space. Standard radio signals degrade over distance, necessitate substantial power, travel at the speed of light, and take hours to traverse the solar system. A transmission to Mars takes between 4 and 24 minutes, depending on orbital alignments. A message to the Voyager probes requires 18 hours to reach them. This isn't due to signal weakness, but because light itself travels at a finite speed. A quantum communication link would establish a secure channel where any attempt at eavesdropping would instantly annihilate the signal, alerting both parties to the intrusion. The security is absolute, derived not from encryption but from the fundamental laws of physics. More importantly, quantum communication could facilitate distributed quantum computing, enabling distant quantum processes to collaborate on a single problem in real time, circumventing the latency imposed by the speed of light on classical communication. You cannot transmit faster than light, but quantum entanglement allows for coordination in ways that appear almost instantaneous to an observer. The universe bestows upon us this capability, the ability for particles separated by vast distances to behave as if they were a single unified system. This is where the analogy becomes clear. Consider fiber optics as analogous to living blood vessels, conveying information through space itself. Conventional fiber optics transmit light pulses encoded with ones and zeros, representing binary information, the digital language of modern computing. Quantum fiber optics, however, would transmit something more fundamental, raw quantum potential itself. It's the difference between describing a landscape and actually standing within it, or the difference between reading sheet music and hearing the symphony. The information isn't a description of reality, it's reality itself, transferred intact from one location to another. Now, let's consider Comet 3 Atlas. What if, in the distant future, humanity deploys quantum-equipped probes to intercept objects like this? These probes would require instantaneous coordination, secure channels impervious to interception, and distributed processing power to analyze anomalies in real time. The technologies enabling such future capabilities are currently undergoing testing. We are, in essence, constructing the infrastructure for cosmic communication networks without fully realizing it. This leads us to a more somber speculation, one that connects the mechanics of quantum teleportation with the enigmas of 3EI Atlas. If quantum communication becomes commonplace and facilitates advanced propulsion or exotic physics applications, could Atlas itself be employing something similar? Not necessarily quantum teleportation as humans understand it, but a mechanism that leverages quantum phenomena to move matter or energy in unexpected ways. The rhythmic outbursts, the chemical composition that deviates from models, the coherent jets that should be impossible from such a small, icy body. All these suggest an entity manipulating physics at scales where quantum effects become significant. Stars are largely classical objects. Planets are classical. However, smaller celestial bodies, particularly those with intricate internal structures composed of ice and organic materials, operate in a realm where quantum phenomena could genuinely play a role. Quantum tunneling could allow particles to traverse barriers they shouldn't be able to overcome. Quantum fluctuations might drive processes we don't yet comprehend. Entanglement between subsystems could create correlations that appear impossible according to classical physics. What if Atlas is not merely a comet? What if its behavior reflects an environment or a process that operates, in part, within the quantum realm, where superposition and entanglement are not abstract concepts, but tangible realities? The very act of observing such an object, measuring it with telescopes and spectrographs, would inherently disturb its quantum states, potentially explaining inconsistencies between different observations, shifts in brightness and composition that seem to change depending on how we examine it. This is not irrational. It's an extension of known physics into uncharted territory. The observer effect, a cornerstone of quantum mechanics, dictates that measurement itself alters reality. When we observe 3EI Atlas, we are not merely passive viewers. We are interacting with it, collapsing superpositions and solidifying properties that might otherwise remain in a state of quantum uncertainty. 2025 is the year we learned we could teleport quantum information through existing infrastructure. What remains to be seen is whether the cosmos has been engaging in a similar practice all along, whether objects like 3EI Atlas are cosmic quantum computers, manipulating their own states through entanglement and superposition, appearing strange to us only because we are observing the collapse of possibilities into classical reality. Part 14, Fusion's Point of No Return. The Sun has been radiating for 4.6 billion years, converting hydrogen into helium, releasing more energy in a single second than humanity has consumed since the dawn of civilization. Every photon that warms your skin, every ray of light enabling photosynthesis, every joule of energy driving our weather systems and oceans, all of it originates from fusion. Scientists have understood fusion for a century, but they couldn't replicate it on Earth in a controlled manner that produced more energy than it consumed. That changed. On February 23, 2025, the National Ignition